Hello everyone, this is Nash. Today I want to share this simple harmonic motion, but in a special case called underdamping. In college physics, you might see this chapter, but usually the textbook will not tell you how to derive the equation. Usually they will just show you the final solution of this underdamping situation. So today I would like to show you how to derive the solution of the underdamping case. For simple harmonic motion, it's quite simple because you will be experiencing no friction, no resistant force. So the total mechanical energy will be conserved. Your amplitude is always the same, and you will keep oscillating as time goes by without any loss of mechanical energy, without any decrease of the amplitude. But if you are now submerged in a viscous fluid, things will be different because when you are moving, you will be experiencing a resistant force caused by this viscous fluid. So how to analyze this kind of motion is a problem. But we can always go back to the fundamental equation called the F equals ma. This is Newtonian mechanics. F equals ma tells you that the ma is equal to the sum of all the forces. If you're now submerged in a viscous fluid, then the friction force is no longer the only force. There's another force called the resistant force. And the resistant forces are usually proportional to the velocity v. And right in front of it, I'll call the b as damping constant. Try to imagine if you're now running, the faster you run, and the more resistant force you will be experienced. So it's quite fair to say that the resistant force is minus bv is proportional to the velocity. So starting from F equals ma, the a can be written down as the x double dot. It means the second order derivative of position with respect to time. And since if I now move into the right, and the friction and the spring force will act on you, and the direction is now pointing to the left. So we get the minus kx and the minus bv. The resistant force and the spring force is always pointing to the opposite direction to your velocity. So that's why you will see the minus symbol right in front of them. So just move all this term on your right hand side to the left, and you will get a differential equation. So the biggest problem for high school students is we don't know how to solve this differential equation, right? You don't know. Even for holiday, for some textbooks, they will just show you the final answer. They will just show you the final solution will be some kind of x as a function of time, and it is pretty ugly. And you can just use it directly, but you never really know how to derive it, right? So today my job is tell you how to derive all this equation, how to solve all this equation, and how do we get the final answer in details. All right. But here's the interesting part. For these differential equations, I can see three variables like the damping constant, the mass, and the spring constant. You get three variables. So I can think of a way to decrease the number of the variables. Like I can name the beta is equal to b over 2m, and the omega is equal to the square root of k over m. You must be familiar with this omega. This is what you learned in simple harmonic motion, right? So you plug them in and you get new differential equations, and simply by observing these differential equations, you only get two variables like the beta and the omega. It's much more simplified. All right. Usually, in order to solve these differential equations, if you are familiar with this differential equation, some people might be able to write down the solution directly. But if you are not that experienced, then maybe you can try to guess the solution. You try to guess the possible solutions. Like I can guess the possible solutions x as a function of time equals a times e to the power of alpha times t. And you might be wondering, why would you like to guess this kind of solution? Why is there any reason? If you know something about the exponential function with the base e, and you must know if I try to take the derivative of the exponential function of e, it always becomes itself, right? For example, like you're trying to take the derivative of the exponential power to the x with respect to x. The exponential power with the base e, if you try to differentiate, if you try to take the derivative of it, of e to the power of x, it always becomes itself. So it never changes. No matter how much time is to try to differentiate the e to the power of x with respect to x, it always becomes itself. Even you try to take the second order derivative, right? So if I want to plug in the solution back into the original differential equations, I hope that the three of them, the three terms, could be quite similar with each other. So they got great chance to cancel with each other. So that's why I guess the possible solutions is some kind of exponential function with the base e, because no matter how many times you try to take the derivative of e to the power of x, it still will be look like e to the power of x. Even though there is some constant like the alpha or beta, if alpha is a constant, you try to take the derivative of e to the alpha x, it just becomes alpha times e to the power of x. They are still in the form of exponential function with the difference of the constant right in front of it. All right, so simply by guessing the possible solution x of t is just like some kind of exponential function with the base e is quite useful because they got great chance to look similar with each other, and they add them all together, they get great chance to cancel with each other. All right, so the x as a function of time equals a times e to the power of alpha t could be the possible solutions to fulfill this equation, right? So let's just plug it in and see what's gonna be. If I plug in x as a function of time back into this differential equations, the x double dot to try to take the derivative of all this term twice. So you get a constant called alpha squared right in front. I can write it down as the a times the x double dot times alpha squared and times e alpha t, and plus the 2 beta times x dot, you take the first order derivative alpha down, so it will become a times alpha times e alpha t, and plus omega naught and times x, a times e alpha t. All this term equals 0. See, all of them, all these three terms, they will get the similar term like a times e alpha t and a times e alpha t, a times e alpha t. They look like each other. So we got great chance to cancel all of them, right? So that's why I guess the possible solutions as a times e to the alpha t. All right, since they'll get the a times e alpha t, I can just take it out. A times e alpha t. And what we are left with on the right column is the alpha squared and plus 2 beta alpha and plus omega naught squared. All right, since it's equal to 0, the a is a constant and the e to the alpha t power cannot be 0. So if you want all this term to be 0, so this column should be 0. All right, and what is it? This is actually a quadratic equation with one variable. This is quadratic equation with one variable. So you can use the formula you learned before when you were young enough as junior high school students. Simply by using the formula, because this is equal to 0, I can say that the possible alpha is equal to the denominator is 2, and the numerator is minus 2 beta plus or minus the square root of 2 beta squared, as 4 beta squared, and minus 4, this is 1, 4 omega naught squared. All right. The 2 could be cancelled. 2 could be cancelled. So the possible, we get 2 possible alpha 1 and alpha 2, right? This is minus beta plus or minus the square root of beta squared and minus omega naught squared. You can see we get 2 possible alpha. I can name it as alpha 1 and alpha 2. All right. Since the possible solutions is A times C alpha t, but I get 2 possible alpha. So these possible solutions can be written down as the A1 times E alpha 1t and plus A2 times E alpha 2t. Our final goal is trying to find out the solution, the x of t. I want to find out the solution, the x as a function of time. Once if I plug in the x as a function of time back into this initial differential equation, so it can fulfill this equation, then I would say this is the solution. All right. So what's the problem if I want to keep solving this equation? How can we keep going? Right? Just plug in this alpha back into this equation, right? You say you get alpha 1 is minus beta plus the square root term, and alpha 2 is minus beta and minus the square root term. Just to plug it in, just plug them in, right? So I'll just write it down on another section. The x of t, you plug in alpha 1 and alpha 2 back into this solution. The x of t is a1 times e alpha 1t. I can be even faster because they all got alpha 1, alpha 2, they all got the minus beta. All right, so I'll just take the e to the minus beta t power, take it out, and times the a1 times e to the square root of beta squared minus omega naught squared times t, and plus a2 times e to the minus because the alpha 2, I say alpha 2 is minus beta and minus the square root term, the square root of beta squared and minus omega naught squared m times t. All right. Pretty tired. Simply by observing this solution, if you don't have the damping constant, that means if you don't have the damping parameter. What is damping parameter? The beta is actually the damping parameter. If you don't have the damping parameter, then it is no longer an under-damping situation. It just becomes a simple harmonic motion. Because if the beta is 0, this is simply 1. If the beta is 0, and all this term will just become very simple. If there is no damping parameter, then the x of t could be some simple harmonic motion solution, like some kind of amplitude and times the cosine or psi function of omega naught t, and plus some kind of initial phase angle. This is simple harmonic motion. But today what we are talking about is the under-damping case. The under-damping case, the beta is not 0. So what if the beta is not 0? Whatever the beta squared is less than the omega naught squared. What will happen? So this is what we are going to talk about. if the beta square is less than the omega naught square, so the beta square minus omega naught square will be less than 1, and you will see I, right? In order to simplify all this equation, I'll just simply let the omega 1 square is equal to the omega naught square minus beta squared. So I can simplify this term. The square root of all this term can be written down as I and times omega 1 t, right? And this one would be minus I times omega 1 t. So keep simplifying this. The x as a function of time is equal to e to the minus beta t and times a1 e to the power of I omega 1t and plus a2 times e to the minus I omega 1t. All right, here's one thing that needs to be mentioned. The e to the power of I theta can be written down as cosine of theta and minus I times sine of theta. It's some kind of useful tool, so you can expand the e to the I omega 1t and e to the minus I omega 1t. If this is I, you can change the positive to be minus. So I want to enhance all this process. So the x as a function of time can be written down as e to the minus beta t. And inside the column is the a1 plus a2 times cosine omega 1t and plus a1 minus a2 times sine omega 1t. We're so close. We're so close. Okay, here's the trick. You can name the a1 plus a2 as some kind of big constant and the a1 minus a2 as some kind of big d constant. You can take them out. Let's see what will happen. I can say all this term is now becoming the square root of c squared and plus d squared. And inside this column, it will become the c divided by the square root term and times the cosine omega 1t. On the right hand side, it will be the d divided by the square root term and times the sine omega 1t. And according to the Pythagoras theorem, I can say this term could be some kind of cosine function or a sine function. If it is cosine, and it will be sine. If it is sine, it will be cosine. I would like to name this as a cosine function. And this will be a sine function. Using the formula, you can combine all this term. You can combine all this term as the cosine omega 1t and minus, because this is plus, minus theta. It doesn't matter this is minus theta or plus, fine, because it's just some kind of initial phase angle. I would like to use the plot symbol. So I can write down, I can even name this square root of c squared plus d squared as some kind of constant a. So the final solution, the x as a function of time, can be written down as the a times e to the minus beta times t power and times the cosine omega 1t and plus phi. Finally. So this will be our final solution to these differential equation when your object is now oscillating inside a viscous fluid. This is under damping situation. And how to understand the final solution. The first term, the a times e to the minus beta t, can be realized as the amplitude as a function of time. For simple harmonic motion, the amplitude is a fixed value. It never changes, because simple harmonic motion will not loses energy, mechanical energy, the mechanical energy will always be conserved because there's no resistant force, there's no friction like this situation. But if you're now submerged inside a viscous fluid, you will be experiencing the resistant force. So your mechanical energy is now decreasing every time when you're oscillating. So it's not hard to imagine that your amplitude will decrease as time goes by. But during all this process, you are still oscillating with the cosine function. So the cosine of omega t plus phi, this is some kind of oscillatory term. So for all this motion, you are oscillating. Yes, you're still oscillating, but with a decrease of your amplitude as time goes by. So your amplitude is a function of time, and is now decay. It shows an exponential decay. So if I plot the solution as a diagram, the amplitude as a function of time is the vertical axis, like the A, as a function of time. And the horizontal axis means the time. And let's say the initial angle phi is equal to 0, then the solution will, starting from some kind of amplitude, and start to oscillate. But with the decrease of the amplitude, so your object is now is still oscillating. Yes, it's still oscillating, but with the decrease of the amplitude, and oscillate with this cosine function. So the amplitude is actually the A of t, and this is A times e to the power of minus beta t. And for the oscillation, this oscillatory term is the cosine function. If phi is 0, this cosine function is cosine omega 1t. So different from simple harmonic motion. Simple harmonic motion, you would not observe the decrease of the amplitude. Simple harmonic motion is they are always having the same amplitude, but with that case of underdamping, you are losing the total mechanical energy. So your amplitude is dropping, but you are still oscillating with the cosine function. So this is the amplitude term, and this is the oscillatory term. All right, so I think the concept is not hard to understand. This isn't a simple harmonic motion, but with a decrease of total mechanical energy. And the most complicated part is solving the differential equations. And as an experiment, you can guess the possible solutions as the a times e to the alpha t, because the exponential function with the base e is quite useful, because no matter how many times you try to differentiate, no matter how many times you try to take the derivative of e to the power of x, it still becomes itself. So if I try to plug in this solution back into the differential equations, all these three terms will have similar form, so they get a great chance to cancel with each other and equal 0. So that's why I guess the possible solution is a times e alpha t. You just simply plug it in and make sure you did not make any mistake, and finally you will get a quadratic equation with one variables. In my mother tongue, it's called 一元二次方程式, the quadratic equation with one variable. By using the formula, you can find out the possible alpha, and the number is 2. You get alpha 1, you get alpha 2, and plug it in. This is your new solution. Since alpha 1 and alpha 2, you know what it look like, so you can plug it back into this final solution, right? We can further discuss the case for simple harmonic motion. If there is no damping parameter, if there is no damping constant, there is no resistant forces, yes, it's actually a simple harmonic motion. It's not hard to find out this final solution. You can try to do it by yourself. But if the beta does exist, and the beta square is less than the omega naught square. And you might be wondering, what if the beta square is equal to omega naught square, is bigger than the omega naught square? We will discuss it later in the future, and that will be called the critical damping or over damping situation. We will talk it later, but today I'm talking about the under damping case. Your object is still oscillating, but with a decrease of the amplitude. All right, if this happens, you can simply by letting the beta, the omega naught square minus beta square as omega 1, and keep simplifying all this, you can get the final solution. The x as a function of time is a times e minus beta t, and this is the amplitude as a function of time. As you can see, because the e to the minus beta t is 1 divided by e to the power of beta t. So as time goes by, all this term in the denominator is now enhancing. So that cause the whole term is now decreasing. So your amplitude is definitely decreasing as time goes by. If you can move long enough, it will stop eventually at some significant point. But you are still oscillating with the cosine function. All right, so this is how we solve the differential equations of under damping case, because if you're a college student, you might open your textbook, but your textbook never tells you how to solve this equation. They will just show you the final solution directly, so you can just accept all this and use the equation directly. But today I would like to show you how to derive this equation. Thanks for watching, and this is Nash.